Hello everyone, welcome to NPTEL Rural Water Resource Management course, week 3, lecture 3. So we have been seeing the key hydrological parameters for rural water resource management, and we'll be looking at groundwater, which is, as I said in my introduction lectures, one of the most important resource for non-monsoon irrigation for rural water. So there is a lot of demand for groundwater. It is by itself a course, but the idea behind the lectures now is to introduce you to the concept of groundwater, and those who are interested can go on further to understand more advanced topics from the books that are given in the course syllabus. So some fundamentals: water that is not taken up by plants and animals and soil moves down due to gravity into the soil profile. And after some more movement due to gravity and percolation, it goes into the groundwater storage. So that movement of water into the groundwater storage is called groundwater recharge. It is very important for rural water management, as I was saying, because during your non-monsoon irrigation season, where there is no rainfall for watering the crops, then most of the water is taken from groundwater. There are dams, large dams that can cater water, but not all areas have dam connections. However, groundwater is almost present everywhere. It just depends on where you are in India and how deep the groundwater is. So as long as you have a bore well logger and a pump and good electricity supply or diesel pumps, you can access the water. Is it sustainable? That's a different question, but access is still available. It's suppose majority of the Rabi season crop, the non-monsoon crop, as I was mentioning, and it is also supplying water for domestic use in urban cities and rural settings, etc. One of the most complex hydrological parameter to estimate and model. So unlike the other parameters, which is either happening on the surface where you can visually see it, then you can recalibrate your models, you can adjust your assumptions. Groundwater is a component that is deeper under the ground and it is not visible, right? Only one or two wells you can see, but between wells you can see a difference in water levels. So if you go to a rural village, you would always have complaints from farmers saying, I put a borewell here, I access groundwater, but my neighbor who just put it right next to my well, there's no water. Okay, and same depths, everything is same, soil is same, the aquifer geology is same, but one farmer is getting water while the other is not. So that is the complexity of groundwater by the way it is set up. So it is one of the most complex hydrological parameters. I would say it is the most, because the others happen on the ground. For example, evapotranspiration. You can look at the plant. If the plant dies, you can assume there's no water loss, right? And if the plant is fully grown, you can know how much at full growth stage the plant grows. But you cannot visualize the movement of groundwater and recharge and discharge. So it is the last step in the hydrological cycle before the water gets into the oceans and lakes. So let's look at it here. The last step, which I mean is the deepest step. So you have precipitation converting into snowmelt, runoff in the rivers, and then storage. So these are early stages. Then some part of the water gets into the system as soil moisture, and that water is taken up by plants. So whatever is not remaining, okay, from this exercise, so like plants have taken the water, animals have taken the water, the remaining water goes down because of gravity, and that groundwater is either stored as deep aquifer water, or it moves back into the system, into the ocean. So it eventually meets the oceans and gives it as a discharge into the ocean. So it is one of the last steps in completing your hydrological cycle. You start from the oceans, go to the atmosphere, come down as precipitation, runoff, go into the groundwater, and then come back to the oceans. Okay. And under that, there's nothing, which means under the groundwater, there's no movement of water because it is hard rock or impermeable surface. So beyond that, water doesn't move. Very, very negligible water, which you can easily say it's negligible. Let's get into the theory of groundwater storage. Once you understand storage, you can also understand the movement. Okay? So soil, rocks, and sediments in the subsurface consist of a matrix of solid minerals and grains. Okay, so this is the solid part of your soil. So as you have soil formation, there are some courses on soil formation. Look it up in NPTEL. What you find is the soil is a weathering process, and on the top of the soil you have purely soil and more aggregate materials. But when you move down, where groundwater occurs, on the top it's soil moisture, down it is groundwater. When you come to the groundwater stage, you see bigger size of soil or rock particles. Okay, and in between them, same like soil, you have void space. Here, air is very less. Okay, so most of the time it is water. So in the groundwater aquifer, you will find almost all the pore spaces are with water. So the minerals and grains have pore spaces, and that is fully occupied by water, which constitutes your groundwater table. So you can see how different materials are. A, B, C, D all have some particle in it, and then a lot of spaces. Okay, so and depending on the spaces, water occupies it, and water is very flexible. It can go through any space. It can manage, maneuver any shape. So it is very lucid, and it can actually be flexibly into any shape. So you can see how it can go into a fracture, which is connected, and all it needs is a connection from one pore to the other pore. So all these pores are connected very slightly. The water fills here. After it fills down, it goes move down to the other pore. Okay, so it depends on the pore space. If you do not have a pore space, for example, here there's no water. Only in the pore space where you have space, water gets in and then stores it. Let's bring the hydrological cycle again to understand where we are. We have precipitation, and whatever water is not taken up by plants after infiltration moves down further downward in the soil profile as percolation, and that percolated water hits a level where it is called the groundwater table level, and underneath that fully the aquifer is formed, wherein all the pore spaces have full of water. Okay, so here you have all the water is being reallocated into all the pore spaces that it can find. And it is the last stage, because below that there is no movement of water. So water moves, goes into the groundwater table. There's no further downward movement, but the water has to come back to a surface discharge. It could be the ocean, it could be the lake, pond, stream, river, etc. There are some instances where water is kept in a pocket, which means water gets in but doesn't get out of the system. Okay, so those are pockets or perched aquifers. We'll look at some examples, and that water is very, very hard to take out because we don't know where it is. It is just a hit and a miss. Okay, it happens because how the earth has been formed. So important parameters for assessing groundwater. We know how water gets in. Now let's look at what are the driving parameters and how can you assess groundwater. First one is base flow. So your discharge curve that we looked in the surface runoff discharge, you could understand what component of water in the stream or the river is given by base flow. Okay, and as we know, base flow is given by groundwater discharge. So by knowing base flow, you can know what the groundwater gradient, groundwater flow. Principles of groundwater flow are given by Darcy's law, and in that the very important parameter is groundwater head, or the elevation of the groundwater level. Okay, so that is the groundwater table, like here. So this from the ground zero to the top is your groundwater level, and that drives your groundwater movement based on Darcy's or Richardson's law. Basically, what it is any water would flow from high potential to low potential, from a higher level to lower level. Imagine you have water in a tank. Okay, to get water to the tank, you use a pump because water cannot go from lower potential to higher potential. So you spend energy to put it up. But when you leave water to stay there, what it would do, it would eventually want to come down. Okay, so water naturally flows from high potential to low potential. So this is the engineered setting. Let's look at a normal setting. So water is happening in rainfall in a mountain region, which is high potential. Water is stored there as ice. Once it melts, it doesn't want to stay there. It wants to come to the low potential, which is your rivers, lakes. So which is the lowest potential? It will come to the ocean. Okay, so that is where if your groundwater table is here and this one, the groundwater table is here, so it will flow from your left to right in this diagram. So that is why you have the arrows here, because the groundwater table here is at a higher potential compared to the groundwater table here, which is at a lower potential. You can see the elevation height, which is given by Head and Darcy's law. The other thing is porosity. How much pore space is available in your material? And that determines the groundwater storage. So once you have groundwater storage, then the water starts to move. Okay, so the process is groundwater is going through a system by first precipitation. Precipitation occurs, it goes into your soil, right? Then it gets stored in your pore spaces, the porosity. Once it gets stored fully, then it starts to move. Okay, so then it establishes a groundwater table and an aquifer concept. Thereby you have movement. Please understand that this is not fully water. You still have solid particles, soil or rock particles here. Only thing is it is all connected. So you can visualize it as a flowing river under the ground. Okay, so here it is like flowing, but flowing means it is connected through the pore spaces of one pore to the next pore. It just flows through. Specific yield is another concept which is very important. It is the drainable porosity. How much water can be extracted from your aquifer is a function of your specific yield. The hydraulic conductivity is the ease by which water can move from one point to the other point. These are explained in the Darcy's law, but we just understand that there is a property which allows the water to move through the system. What will it be a function of? If we look at the concept of groundwater, it is stored water in the pores, which means there is still solid material and it is interconnected. Okay, so all this is a property of the soil. So the hydraulic conductivity or the ease by which water can conduct between a pore and another next pore is given by hydraulic conductivity, is a property of the soil. Okay. Groundwater recharge is a very important aspect to understand groundwater assessment. Groundwater recharge can happen naturally by infiltration, percolation, etc. But sometimes it is not enough. It is very, very slow. And the farmer wants the wells to recharge for the next irrigation. So what do? We have augmented and artificial recharge. So the well, which was initially dug for domestic use to drink and for cattle, slowly began to be used for irrigation. And then the number of wells multiplied. So all this is having a tremendous impact on the groundwater sustainability, because groundwater is a very slow process. It has to go through the soil, the rocks, the pore, etc. But then you easily extract it using a pump. So to increase the groundwater level, people would do augmented, which means additional structures or artificial structures to recharge. Then the concept of aquifer. So here, this is your aquifer. Okay, aquifer is the level at which water has been connected and water flows through the aquifer. Okay, so this part would be your aquifer. If you have a no permeable layer, which means a big rock or something which is separate the top and the bottom, then you can have an aquifer on the top also, because there is no flow on the bottom and water can flow. And inside, underneath here, there's another flow which happens. So you have two aquifers, like a layer cake. Okay, you have a cake, and then some cream, and then a cake. Look at the cream as a non-penetratable layer, which water cannot go through. So water will flow through the cake, then no flow, and then another. So they have two aquifers. Let's start with the different types of groundwater. So there are multiple different types of groundwater aquifers, and all aquifers can be explained in this cross section. So what we have here is precipitation, which is the recharge for all of the groundwater resources. Okay? And first precipitation occurs into a land, and then it starts to move down. While it moves down, it faces impermeable surfaces at different levels. So here we have the bedrock, which is impervious, which means water cannot move through. So water would move in a lateral way. So from vertical, it goes horizontal. Similarly, the top surface, which is your land surface where infiltration happens, water moves down, and then slowly it sees another impervious layer, which is not as highly impenetrable like your bedrock, because bedrock is the deepest you have, while this one is not as strong in penetration. Okay, so you have water coming in and it hits your impervious layer. Okay, impervious layer, then what happens? Water starts to pond up. While water starts to pond up, your soil gets, or the soil or the solid particles, the pore space gets water. So number two, what you see here is called the zone of saturation, which means the water is full. Remember the soil moisture we discussed? Same here, your zone of saturation is a fully watered with full of water aquifer. So this becomes your water table aquifer. What about the water which is moving in the soil and coming down? That becomes your zone of aeration. So you have a water aquifer which is formed, and right on top of it, you have a zone of aeration which can still take water and become saturated. Okay, so those are the two types you have: zone of aeration and zone of saturation in one aquifer unit. Then you have your confined aquifer. So this is an unconfined aquifer, which means on the top, you don't have an impervious layer. You can still infiltrate water, and you can still convert the zone of aeration into zone of saturation. Whereas this layer between two impervious layers, so impervious layer 1 and the bedrock, the layer of soil or weathered rock which has water is a confined unit. It is confined between two impermeable layers. You get the point? So water can flow, get in, but it cannot go up or down because it is confined within that unit. And these are much deeper aquifers. In other terms, this is called a deep aquifer, whereas the top one, which has still potential to recharge, is called a shallow aquifer. In hydraulic terms, we call it zone of aeration and zone of saturation. And then different wells can be put to access the water. So in a zone of aeration and a zone of saturation, you can have shallow wells where you can drill down and take the water. Whereas you can take a water from your confined unit with deep bore wells. And the deep bore wells can have a screen here to just take this water, or two screens on the top and the bottom to take the shallow aquifer and the deep aquifer. If you're a farmer, you would like to have all the water coming into the well, right? Not just one water. But if this is polluted, then you would screen the well and only open the screen here so that your deep aquifer is giving you water. So the shallow groundwater is the water which we have used in a well. So when you see a pulley system in a well, those are shallow aquifers, shallow groundwater, where water gets recharged annually, and it can be used for domestic and irrigation purposes. Whereas the deep groundwater has taken a long time to recharge because it is not as ready as infiltration, percolation, than groundwater. It is recharging somewhere else and then coming here. See here, this water can be vertically recharged. But for this water, it has to come from a very, very far distance. So the deep groundwater is a water much, much older than the shallow groundwater. And then on top of this, you have a locked groundwater, which is called a perched water table, which means in your soil, sometimes you have a confining unit like a bowl or a small shape where water can get in, but it cannot get out. Okay, so which means downward movement cannot happen, but water can get on the top. So that water is called a perched groundwater, and that is a locked groundwater where it cannot move laterally, but once it gets filled, it just gets saturated. So this is where I was saying a farmer can put a well here, and in just 30 meters, he can get water. Another farmer, which his house is here, which is very close to the other, he'll build at 30 meters, he won't get water. He'll still have to go down. So this understanding is not available for farmers. They cannot understand it. How come you put a well there, you get water, but just 10 feet away, I'm not getting water? It's because of the complexity inside the ground. We do not know where this impervious layer will form. There's no idea how it forms. Okay, I'm saying you cannot model where it forms. So you'll have to be careful in understanding these externalities in groundwater. So these are the three different types of groundwater. As after water moves in, you have your shallow groundwater, then you have your deep groundwater and locked groundwater. So all these are based on your hydrogeology, the rock material that is present in India. And this has been given by the Central Groundwater Board, the map, and there is not much change between years because the rock is a rock, right? You don't change the parent material that easily. It can weather as soil. So groundwater moves through the soil and then moves through the hydrogeology, but the geology still stays. Okay, so what you see here is the different types of aquifers based on the geology of India. And you could see that this part where you have unconsolidated formations or more unconfined aquifers, alluvial aquifers, you can find a lot of water. So the yield is pretty high. You see high yield in liters per second and in the deep blue color. Okay, so all the basins or all the areas with a big river network, you could see a good groundwater availability in terms of yield. And here on the coastal regions also, because all these central flowing rivers would come and deposit here. So all the sediments would give you a good aquifer, alluvial or sediment aquifers. Then we have the consolidated or semi-consolidated areas, which is most of central India, where you have deep aquifers. Most of it is deep aquifers because the formations do not happen every day. Here, every day you have sedimentation. So you have an aquifer which is being built up, whereas here it's not that frequent. Okay, so these are the unconsolidated aquifers on the rivers. Then you have in central India more consolidated or semi-consolidated. Some rivers are flowing. So you have consolidated and semi-consolidated aquifers, wherein the yield is much, much lesser compared to your unconsolidated formations. Then you have hilly areas, almost very negligible water because water doesn't penetrate in. Your hill is just a rock, right? Mountains are rock. So where is the pore space for the water to be stored? It's very less compared to a soil where the soil has air and pore space. Your rock doesn't have that much. So when you pour water on a rock, it just falls down. So that is where you have less yield in groundwater. So now you understand that for groundwater, you need to understand your precipitation. You need to understand the soil and the type of soil, which gives you the details of porosity, hydraulic conductivity, etc. Then the geology to understand the deep aquifers. And if it is a hilly region and rock, there's not much water that will be stored. So if you look at mountains and stuff, you might get good rainfall, but you need to capture the rainfall for agricultural domestic use because groundwater potential is very, very low. And even drilling into a mountain area is very hard, right? Because it's so rock. So it is very hard to even get your drill down. How do you determine groundwater recharge? Mostly it is because of its complexity. Mostly it is made by your groundwater budgets. So if you know the groundwater resources are determined by your precipitation and runoff, you can calculate your infiltration. So let's look at some of the Groundwater Estimation Committee's 1997 report, which is still used now because it's just a formula. You have infiltration, which is the water that gets into the soil, and that is the water which goes to percolation and your groundwater recharge. So infiltration is kind of the first step in your groundwater recharge. So you could see it as, it can be very simple as precipitation minus runoff. So precipitation is the water coming in, and runoff is the water that goes off the system. So the difference gives you the volume which actually infiltrates. Okay. Then you have your evaporation. Then you can add on your evapotranspiration, which means you can make your equation more complex by throwing in more and more variables. And by on, you can actually add your groundwater, you can actually snow melt, runoff, or your ice, etc., etc. Infiltration, storage of water. So all this can be done at different scales, regional or sub-regional scales. And you could also look at different methods suited to your land. So for example, in your land, if there's no agriculture, or if there's no transpiration happening or no water bodies, then most of it is going to be precipitation and runoff. So after runoff, if you can capture the water and understand how much runoff is there, and if you can capture the rainfall, understand how much rainfall is there, the subtraction will give you your infiltration, more or less, right? So these are the different methods, and based on this, there are a lot of models that estimate groundwater. There are satellites right now, but we will not get into that because it is not at a rural scale, the satellites for groundwater. So I'm not including that in this picture. Someone might ask me tomorrow, sir, do you have groundwater recharge based estimations from GRACE satellite, which is NASA US satellite. But I do that for a state level or country level, not for a village level, right? Because at village, it is such a small and the resolution is not good. So how do you estimate groundwater recharge is by looking at your wells, understanding the hydraulic conductivity, understanding the properties of the soil. You could estimate, back calculate your recharge by these kind of methods. It is very expensive to do everywhere monitoring by groundwater. So groundwater board, the central groundwater board, which you see here, is the authority in India to have these monitoring wells and regularly gives you data once in every 3 months at least. So quarterly you get data and across India, they have around 15,000 wells, okay, to monitor and give you the data. So I think every year they do add more wells, and it is a very, very time consuming and costly affair to get the groundwater data. So you don't see too many estimations. Okay, so somewhere you need to model it, somewhere you need to estimate it based on your precipitation and runoff, and somewhere you would estimate it based on your characteristics of the geology, like we saw here. The geology. If I know the geology, I could estimate how much porous space is there. From the porous space and the rainfall, I could estimate. For example, if the Ganges was not flowing, there's no water there. Either you have porous space, but you will not have water, correct? So based on your runoff, based on your precipitation and your soil and geology characteristics, you can estimate groundwater recharge and groundwater storage. Driving home message is, please understand there are multiple groundwater wells or groundwater storage, and what a farmer uses might be shallow aquifer initially, but as the water level goes down. So for example, if the water consumption is high, the water level will keep falling. And after this water is totally used, then this well becomes abandoned. He or she would drill another well, much, much deeper, and get water. That could be a deep groundwater aquifer. So driving message here is, it sustainable if you just keep on drilling deep and deep? So all of you will notice that even in urban centers, you start with a well depth, and then suddenly after some years there's no water, you drill deep, then you drill deep. And because you know that as you go deeper and deeper, there will be some water based on this diagram. But once you hit bedrock, there's no water. So it is not sustainable to keep drilling Sustainable way is to increase your recharge, increase the groundwater flow so that you can store more water and reduce your consumption. If you know that you cannot grow your crop, why are you going to use the groundwater? Right? So you might use it in 3/4 of the time. For example, if your crop needs 10 irrigation schedules, your groundwater can give water for 3. But what about the remaining 7? And if you don't have water for the 7, your crop is lost. So the idea is to understand how much groundwater you have before using it. And depending on that, you use a crop or an area of crop for watering. So please understand these 3 different types. The locked groundwater can be misleading because you'll find water, you'll be happy, but it is such a small component. And your shallow groundwater would eventually lead to a deep groundwater access. So this is the problem in India currently. We will get into the rural issues when we go into the groundwater lectures in the future. I would like to stop here. Thank you.